Let's jump right into this explainer with a seriously mind-bending thought experiment from Quantum Magazine about the true nature of, well, nothingness. We're going to explore a concept that totally shatters our everyday intuition about empty space. It's this massive mystery sitting right at the crossroads of quantum mechanics and the cosmos.
Imagine you've got just a standard cardboard box. Now, applying some wild sci-fi level technology, you seal it up and pump out all the air. But we're going further. You meticulously strip out every single rogue atom, every stray photon of light, and you even manage to evacuate unseeable stuff like dark matter. You've eliminated absolutely everything we conventionally understand as stuff. So what's actually left inside that box? Now, common sense screams the answer is just nothing, but it turns out the universe absolutely abhors a true vacuum.
Because quantum mechanics tells us that your meticulously empty box is actually still full of energy. Physicist Peter Maloney beautifully describes this state not as an empty void, but as nothing infused with the potential to be anything. It's fascinating. Even without a single electron present, the vacuum possesses this inherent electronness, basically the baseline potential to create any particle. So all your intense efforts to completely empty the box, yeah, they haven't even put a dent in this underlying energy.
The empty box mystery, evolving the concept of the void. To understand why you can never truly empty a box, we have to look at how physics has radically changed its mind about empty space. In antiquity, the Aristotelian idea of an absolute void, space entirely independent of body, was philosophically rejected just on the premise that nature abhors a vacuum. But fast forward to 1911, and Max Planck discovers what he calls zero-point energy. He realized that even in their lowest possible energy states, molecules and crystal lattices retain the subtle, completely unavoidable vibration. Then, boom, in 1917, Albert Einstein introduces the cosmological constant into his equations for general relativity. This laid the groundwork for a vacuum that isn't just empty space, but a physical entity with its very own energy and pressure.
A seething sea of particles, the quantum vacuum.
So how exactly does modern physics define this energetic nothingness today? Well, quantum field theory doesn't treat space as an empty room where particles occasionally visit. Instead, you've got to think of space as a three-dimensional infinite grid of invisible vibrating balls and springs. And because of Heisenberg's uncertainty principle, that fundamental law where you can never know both the exact position and momentum of a system, those theoretical balls and springs can never, ever be perfectly still. If they were, their position and momentum would both be exactly zero, and Heisenberg strictly forbids that. This constant, unavoidable jiggling creates a baseline residue of energy called ground state or zero-point energy.
Crucially, this zero-point energy isn't just some abstract mathematical concept. It manifests in our universe as a seething sea of virtual particles. These are pairs of particles, think an electron and a positron, that are continuously popping into existence right out of the quantum vacuum and then instantly annihilating each other and disappearing. They essentially live on borrowed energy for just a tiny fraction of a second. But this constant, frantic bubbling leaves a real, measurable signature behind on the fabric of reality itself.
Proving the vacuum. The Casimir effect.
If all of this sounds like purely theoretical math, you're probably wondering how we can actually prove this invisible, seething energy exists. Can we measure something we can't see? Well, in 1948, Dutch physicist Hendrik Casimir predicted a tangible physical force based entirely on this quantum weirdness. He realized that if you took two electrically uncharged, perfectly conducting metal plates and placed them incredibly close together in a vacuum, the zero-point energy of the electromagnetic field would actually push them together.
Here's why this happens. The plates act like a physical guillotine for the quantum vacuum. Between the tightly spaced plates, only virtual photons with short wavelengths can fit. The longer wavelengths, they're simply excluded, totally chopped off. But outside the plates, out in the vastness of the surrounding vacuum, all wavelengths are present. This means the overall energy density of the vacuum outside the plates is actually higher than the energy density inside that tiny gap. And this difference in energy creates a literal, physical pressure that pushes the plates together. It's literally force from nowhere.
And this wasn't just a fun thought experiment to chat about at physics conferences. Decades later, in 1997, a physicist named Stephen Lamorrow built an incredibly delicate torsion pendulum and definitively, quantitatively measured this Casimir force. He verified it to within 5% of Casimir's original theoretical prediction. He proved beyond a shadow of a doubt that the vacuum exerts a real physical push.
Now, as we explore this explainer, we do have to impartially look at the whole picture, and there is a caveat to note.
In 2005, R.L. Jaffe published a paper arguing that the Casimir effect, while absolutely real, could mathematically be derived from the relativistic quantum effects of currents and charges within the metal plates themselves. So in his view, it doesn't absolutely require the existence of vacuum fluctuations to be calculated. That being said, within the broader context of quantum field theory, the zero-point energy framework remains the most widely accepted and arguably the most elegant explanation for the phenomenon.
The cosmological constant problem, the record scratch.
Assuming vacuum energy is real, and again, the vast majority of modern physics relies on it being real, we crash headfirst into what is widely considered the single most embarrassing miscalculation in the history of science. As physicist Sean Carroll points out, thanks to Einstein's E=mc², we know that mass and energy are basically two sides of the same coin. Therefore, all forms of energy create a gravitational field. You literally cannot ignore it. If empty space is packed with zero-point energy from all these fluctuating quantum fields, then the vacuum of space itself must have a gravitational pull.
But when we compare the math to reality, we hit a massive, universe-breaking paradox. On one side, we have quantum field theory. When physicists sum up all the zero-point energies of all known fields, the math predicts an insanely huge, gargantuan amount of vacuum energy. We're talking potentially more energy hidden in seemingly empty space than in all the stars and galaxies in the observable universe combined. But then, on the other side, we have cosmological observation. When astronomers actually look at the universe, they observe an accelerating expansion driven by a tiny, almost imperceptible trickle of vacuum energy, which we usually call dark energy.
To really put that quantum field theory prediction into perspective, the theoretical calculation of vacuum energy density scales all the way up to the Planck limit, resulting in roughly 10 to the 110th power giga-electron volts to the fourth. That is a 1 followed by 110 zeros. It is a number so unimaginably huge that it's around 120 orders of magnitude larger than the dark energy we actually observe. It's often called the worst theoretical prediction in the history of physics, and for good reason.
Think about it. If the quantum math were completely right about the scale of this energy, the gravitational force would be utterly catastrophic. As early as 1946, physicist Wolfgang Pauli realized that this much zero-point energy would create a gravitational field so intensely strong it would either instantly curl the universe up to a microscopic size or blow it apart so violently that galaxies, stars, and planets never even could have formed. Obviously, since you and I are here observing the universe, the math and the reality are just wildly out of sync.
Can we harness it? Tapping the void.
Now, taking a step back from total cosmic doom for a second, given that there is theoretically so much energy hidden in empty space, you might logically wonder, could humanity ever plug into the vacuum? Like, could we solve the global energy crisis with an empty box? Well, physicist John Boz humorously notes that while some eccentric folks get really excited about zero-point energy machines, the rigorous reality of thermodynamics gives us a hard no. By definition, zero-point energy is the absolute lowest possible energy state of a system. To extract energy and do useful work, you have to move energy from a higher state to a lower state. Because the vacuum is already at the absolute bottom of the ladder, there is nowhere lower for the energy to go. So trying to extract this baseline energy to power your toaster? It's fundamentally impossible according to the laws of physics.
The future of nothingness. Bridging the gap.
So, if we can't harness it to save the world, and our mathematical calculations are astronomically, embarrassingly wrong, how do modern physicists actually solve this cosmological constant problem? Well, they've come up with some wildly creative proposed solutions. First, there's supersymmetry, which suggests every particle has a hidden partner. Since fermion fields contribute negative vacuum energy and boson fields contribute positive vacuum energy, the idea is maybe they just perfectly cancel each other out. The only problem is the Large Hadron Collider at CERN has found exactly zero evidence for supersymmetry so far. Then there's vacuum energy sequestering. This is a theory proposing auxiliary fields that effectively hide this massive energy from gravity. And finally, we have mind-bending theories like microcyclic universes. This suggests that down at the microscopic Planck scale, space-time is this wildly fluctuating foam constantly expanding and contracting. This rapid chaotic oscillation effectively hides the massive energy from the macroscopic observable scales that we live in.
And that brings us to the ultimate question. As we've seen, the vacuum isn't empty. It's a roiling, energetic foundation of reality that we are still struggling to comprehend. Resolving the staggering mismatch between quantum mechanics and cosmology isn't just about fixing a little math error. It leaves us with this profound realization. Resolving the mystery of nothingness Understanding why the vacuum energy is exactly the tiny precise amount that it is might just be the exact key we need to finally unlock a theory of quantum gravity, and with it, the true origin of everything. So, what else is hiding in the empty box?